Okay, David, you can go ahead.
Okay, thank you very much, Denise, and thank you for joining us. Again, today's focus is going to be on essentially detecting hydrocarbon migration pathways in seismic data. In seismic data, what we see as vertical hydrocarbon migration pathways are these zones of sort of diffuse, low coherency data that is often reduced in amplitude, and they are generally called gas chimneys, gas clouds, or sometimes hydrocarbon-related diagenetic zones. And what we're going to show today is a means using OpendTect to detect these migration pathways in seismic data. And through this, we will be able to then visualize them in 3 dimensions and see the origin of the chimneys in deep reservoirs or even in the source rock, how they migrate into shallow reservoirs, and then how they leak from these reservoirs to form a surface expression of hydrocarbon seepage. Again, the outline of the presentation today, I'm going to touch briefly on the purpose of gas chimney processing, but I'm really going to focus today on the methodology of how we do this in OpendTect, and then again focus on how we validate the processing results that we get, and then touch briefly on the applications and exploration. The purpose of chimney processing is essentially to distinguish subtle hydrocarbon migration pathways from other features, other vertical discontinuities in seismic data, such as polygonal faulting related to dewatering or debris flows, which can look a lot like gas chimneys. Again, a lot of times in seismic data, these are not able very simply to distinguish in the data. And through gas chimney processing, we can detect these deep, often deep thermogenic hydrocarbon migration pathways and distinguish them from other aspects in the seismic data which may be not related to hydrocarbon migration. Again, another purpose is to be able to distinguish these features in 3 dimensions, and thus we can look at their morphology. In this way, we can distinguish diffuse gas clouds from more point-sourced features like blowout pipes or mud volcanoes. And again, we can make inferences about seal and so forth from this, in that a lot of times when we see these diffuse gas clouds, they indicate very modest flux rates, where these mud volcanoes or blowout pipes may represent higher flux rates of hydrocarbons. From this information, again, we can link our reservoir Geo Bodies to our chimney features and understand the actual charge of our reservoir, either prospects or leads, and also see how these reservoirs are leaking hydrocarbons, and look at seal, basically vertical seal risk. Again, the methodology. The single attributes, be them amplitude, normal seismic displays, similarity or coherency, can image these gas chimneys. However, individual attributes have a lot of overlap, and so they will image things that aren't gas chimneys as well. So what we want to do is use a neural network to essentially combine these different attributes and distinguish the feature of interest, the chimney or the salt. Again, the software we're using is OpendTect, and we're using 2 commercial plugins to OpendTect, which are the dip steering plugin and the neural network plugin. The methodology that we will use, first of all, again, this can be done on both 2D and 3D data, but we're going to focus on 3D since the reliability of the workflow on 3D is much greater. First of all, we will scroll through the 3D seismic data and find examples of the best examples of what we suspect are highly reliable gas chimneys. The features that we're going to look for are these zones of chaotic, often low frequency data associated with shallow amplitude anomalies, and then hopefully if we see any leakage to the surface, we will see associated mud volcanoes, pockmarks, other features that indicate that these are reliable chimneys. And again, what we want to do is pick examples of these most reliable features for neural network training. The second thing we need to do is to actually pick examples of these chimneys using in the OpendTect the pixet polygon. What we're going to do is create a new pixet, and again we'll use an empty pixet, and we will pick examples of chimney yes and chimney no. And the key thing for chimney yes is to pick in areas where we see good evidence of chimneys, pick a lot of examples so that the neural network has a lot of features to train on. And the key here too is to, when we're picking examples of chimney no, is to pick examples in faults that are maybe crisply imaged, and also in areas that we don't see evidence of vertical migration but might represent low amplitude, low similarity features. Again, so that we can use the neural network to distinguish the valid chimneys from these features. Oftentimes we may have examples of salt in the data, and of course you can pick examples of that as a chimney no. However, a lot of times it's very difficult to distinguish salt from chimney, so that you may want to use that as a separate pixet and be able to either use those examples or not. The other thing in terms of setting up these pixets is you may want to label them by the line that they occur on, so then if you need to edit them later, you can know where to go to find them. Once you've selected these representative train locations, you want to select a set of seismic attributes that can essentially distinguish the gas chimneys. And what you want to do there is to go into the default, or go into the attributes window and select the default attribute set called NN Chimney Cube. And this again will bring up a whole list of attributes which have been seen to be useful in distinguishing chimneys. And again, a lot of these attributes will be similarity attributes, which measure the similarity from trace to trace of the feature. And again, we will look oftentimes up 100 milliseconds and down 100 milliseconds because chimneys tend to be vertical features. Again, in contrast to faults, which may occur at an angle, chimneys tend to be vertical. The other thing that you'll see in here is some attributes that basically measure noise or signal to noise, because again, chimneys tend to be very chaotic. Other attributes in this default attribute set are two-way time. And again, two-way time can be used because the character of the chimneys may change as you go deeper. However, if the type of data, if you just pick shallow chimneys and use two-way time, you may bias your data set. So in the first stage, I would not use two-way time as an attribute and only use it if it's useful. The other thing is that you'll see a number of frequency attributes, because a lot of times we see a drop in frequency in these gas chimneys due to attenuation of high frequency. And so we have what's called a frequency washout ratio, which is a ratio of the low pass and high pass RMS amplitudes, which sort of measure that type of frequency over a broad window. Again, because these chimneys tend to occur over broad zones. Again, once you have a default attribute, you can then go in and create a neural network. And again, you go into the neural network portion of OpendTect and go into what's called Create Neural Network. What you're going to do is do a supervised neural network, meaning that you're going to actually pick examples of what is a chimney or not a chimney. And so you're going to use that pick set, chimney yes and chimney no, as your supervised elements. The other thing you're going to do then, in the first stage, it would be to actually use most of your attributes except the ones that say no neural network input. Those are sort of attributes that have been used to create other attributes. But essentially you want to use most of those attributes in the first stage and see which attributes are actually important in the neural network training. You can then, once you know those, you can then cut down your number of attributes later to a more manageable set. However, I recommend that you run over 10 to maybe 15 attributes, because the neural network will have better results with a large number of attributes. The other thing you do is set aside a 20% set for testing those attributes. Once you've created your neural network, you begin training. Quickly as you begin training, and again, the neural network will have a drop in normalized RMS, and you'll have a drop in the number of misclassifications. And so what you want to do is then run these until you begin to get a separation between the train and test data set. And when you begin to get that separation, it means you've overtrained and you want to stop. Again, once you've done this, you can, if you have any results that don't look good, you can add new test sets. So the next point is to apply this neural network to the data. What you want to try to do is get a good match between what you have determined to be high probability chimneys and a high probability of chimney from the processing. The training goes from 0 to 1, which means low probability to high probability. Overlaying this on the seismic data, and when you get a good match, then you can be satisfied with the neural network results and apply it to the whole volume. Once you have a 3D volume of chimney probability results, you can visualize it in 3 dimensions using the 3D visualization tool in OpendTect. Another thing that we can do in the 4.3 version of OpendTect is detect Geo Bodies. And this has the advantage of being able to categorize some of your geobodies. You can detect them based on a point source where you see what are interconnected geobodies, in this case interconnected chimneys, and you can then classify them by where they originate, so that if you have biogenic gas or chimneys that are originating in the shallow part of your section, you can give them a different color and then view chimneys that say originate from the Cretaceous versus chimneys that originate, say, from the Eocene, and categorize your geobodies in that way. You can also take unreliable geobodies and give them a lower probability. One thing we see is that not all vertical discontinuities in seismic data really represent hydrocarbon migration. Thus, we need to validate the processing results. There are a number of other causes of vertical discontinuities in seismic data, some related to seismic imaging and some related to geologic features, which can be confused with gas chimneys. So we have a set of criteria which we can then use to assign a reliability to the chimney results. What we want to do is really ask three main questions. The first question is, are the chimneys due to fluid migration or just poor seismic imaging? A lot of times related to faulting, you may have poor imaging that could be related to velocity contrasts across the fault, be it a fault shadow, or other features like salt can cause poor imaging that are not due to hydrocarbon migration. What we want to do, the criteria for distinguishing that, is a pockmarked morphology on time slices, which often occur at fault bends or intersections. An example that we can show here is from the Gulf of Mexico. This is sort of a typical example. We have a fault which is very shallow and goes deep and is related probably to some deep salt. And so what we don't know is, in this zone right here, are we looking at hydrocarbon migration or just poor imaging? And you do see some migration smiles and other features that suggest there's some poor imaging in this section. However, we do know from these amplitude anomalies that we are dealing with hydrocarbon migration in this area, so we suspect that indeed we are dealing with chimneys. So what we're going to do is a time slice, in this case above the objective reservoir and below the objective reservoir, to look at the morphology of the chimneys. The thing we look at when we see the chimney processing results on a normal seismic line is, yes, we see higher probability chimneys in this zone, but we really don't know whether these chimneys are reliable. The time slice, in contrast, we see in the section above the reservoir, we see a very linear fault, which is basically low probability chimney. And in the zone where we see suspect the gas chimneys, again, we see these pockmarks, which are at fault intersections and give us more confidence that these represent fluid migration. However, just because we see fluid migration doesn't necessarily indicate that it represents hydrocarbons. So the second question we need to ask is, are those chimneys really related to hydrocarbon migration? And a criteria we have for that is, do we see a link between the chimneys and shallow DHIs or carbonate buildups? When we have fluid migration, we may see these pockmarks, but we won't see the shallow anomalies or the chemosynthetic buildups related to features, biologic communities feeding on the hydrocarbons. So again, these DHIs are very useful, even in areas where the deeper section may not have valid AVO. Another criteria is just, do we see a link between the chimneys and a deep source rock? The areas where we see fluid escape, in this case these lower probability chimneys, do not originate from a deep thermogenic source, and thus we can interpret them as being due to fluid escape. Another criteria is a link to surface geochemical data, or in the case of offshore data, piston core information, which will indicate a thermogenic source. Finally, basin modeling is a very good tool, and when we see a correlation between evidence of vertical migration in chimney data and in basin modeling, we have a much higher confidence in both the basin model and the chimney results, remembering that basin modeling, because it is measuring examples of, due to pressure contrasts, the results are coming from totally independent sources. Finally, we can ask if the chimneys are related to thermogenic hydrocarbon migration. Another criteria we can look at is, do the chimneys correlate to mudlog shows? Anytime that we drill through a show, C2 through C5, or an oil show, we should be able to see a link between that show and a deeper chimney, or actually in a source rock itself. And this is very common. These examples from the North Sea, we see an increase in C2 through C5 in the chimney itself, an increase in pressure, and we can correlate that to the example of our gas cloud or gas chimney. Given these results, we can then high grade individual chimneys, give them a reliability rating, and visualize them in that respect. The applications then we can use this chimney results in exploration include looking at, we can actually take mapped faults and look at how display the chimney results on those mapped faults. We can actually see which parts of a fault surface are migrating hydrocarbons and which parts of a fault are not. And we will often see that these occur at fault intersections and at bends in the fault. We can visualize these in some instances in 3 dimensions and see the link between those and pockmarks at the seabed. Again, this gives us a very good idea for risking fault leakage and seeing if we have a reservoir intersecting a fault at an area where the reservoir may be charged, or if it's a channel, it may be intersecting a fault at an area where it might not be charged. The other thing we can do is use this chimney information to predict the top of abnormal pressure. What we have recognized, but we're still in the early stages of understanding completely, is that gas chimneys represent fracturing and pathways for deep pressures to be moved shallower in the section. Thus, if we look at where the top of a chimney is, a lot of times it will correspond to the top of pressure. However, a lot of times when we are making pressure predictions, we use velocities that are in a sort of normal area, and a lot of times we may miss some shallow pressure targets for that reason. This is an example where we see a gas cloud in this area that corresponds to the top of pressure. The results of chimney processing show as we drill through this normally pressured section, in this case 10.5 pound per gallon mud, as we drill into the top of this chimney, we go from 10 pound per gallon to 14.5 pound per gallon mud weights, and a very severe top of pressure. Again, chimney analysis can be used to predict, or at least help predict, some of these pressure zones, and can be used in a safety program. Another thing that is very useful, as I've sort of alluded to previously, is that we can use chimneys to risk hydrocarbon charge into a prospect. Very often in fields we see chimneys in the section below the reservoir, immediately below, directly charging the trap. This is very common in the Gulf of Mexico, and we can assign, when we see this, we can assign a very low risk to hydrocarbon charge. Oftentimes too, we may see a reservoir that is linked to a chimney. Again, we can assign very low to maybe moderate risk for these type of hydrocarbon charge. The major issue is when we see minor chimneys associated with a reservoir or a lack of chimneys, we see moderate to higher risk for hydrocarbon charge. The other thing we can use chimneys for is to assess vertical fault seal risk. The other thing we see with very often is what I would call these fault seal traps, where we see migration up into the reservoir but a lack of leakage above the reservoir along faults, again, which may either be connected or not directly connected to the deeper faulting. These fault seal traps have a very low risk. In contrast, when we see leakage along the fault, the trap-forming fault, we have a more moderate to high-risk chance. And when we see chimneys on the flank of a feature, we have a very low risk, and often these are filled to spill. The challenge is to distinguish these fault seal traps from these fault leak traps. There will be a continuum of examples of major leakage versus minor leakage, so we can use the overall morphology to assign risk for vertical fault seal. Finally, the other thing we can look at in areas where faulting isn't as important, we can look at vertical top seal risk. And work that has been done by Rohr Heglund and others at Statoil shows that there is a distinct difference in risk between these gas cloud traps, more diffuse zones of leakage, versus these point source traps related to either blowout pipes or mud volcanoes. And their work in the North Sea primarily shows that you can risk these very differently. Basically, gas cloud traps are a very positive indication, where these point sourced are fault-related leakage or a higher risk. Again, if you're starting a chimney project, as I sort of pointed out in this webinar, experience is very critical in doing chimney processing. And of course, what we want to do is for you to have success in a project so that the reliability of this technology is as high as possible. For that reason, we recommend training in this technology. We are more than welcome to help you with consultancy or doing a chimney project to start out with, so that the results of these chimney processes are extremely reliable. We don't use the technique in areas where seismic data is not appropriate, and that you have success in the results, and it's useful in assessing risk for your prospects or assessing fields that are in the area. So if you have any questions about this, please contact us at our office here in Houston or in Enschede, and we would be glad to discuss this with you. At this stage, I'd be glad to open this for any questions.
Thanks, David. That was a great presentation. Please, if you have any question, raise your hand, and you can say your question after that. Okay, David, I send you a question from Eric. Okay. Can you see it? Yeah. Okay, go ahead. Can you read it for the others? And
question. Hold on a second. Okay, I'm getting it here. Okay. The question was, hold on.
The area of salt.
Yeah, the areas of salt was not selected for chimney yes or chimney no. How will the results of the neural network will look in that salt area? What I have determined is very oftentimes salt will give a high probability of chimney. However, in certain areas where you can process, we can actually distinguish the salt and the chimney. And so what I like to do is use a pick set to pick examples of chimney yes, and then I use that in my neural network as, I pick areas where you say salt yes, and use that in your neural network to indicate as chimney no, and then see how your results do. If you get a distinction between salt and chimney, then you would use those pick sets. If the neural network training is poor, then you may want to keep the salt examples out, and then you will have some ambiguity between what is salt and what is chimney. What we recognize very commonly in both the North Sea and the Gulf of Mexico and in some of the basins in Brazil is that you get, because of the movement of the salt, we will get chimneys associated with that salt movement. So very commonly on the flanks of salt, we will see good evidence of chimneys. So what I want to do is make sure that I don't eliminate those features. But again, a lot of times you may have some ambiguity about what is salt and what is chimney.
Okay, you have another question from Nicola. Nicola, would you like to read your question?
Yeah, how do you distinguish between volcanic intrusion related chimneys and hydrocarbon related chimneys?
that may be just difficult.
Okay.
Okay, any other question? Farouk, you said you have a question, I think?
No.
I guess one thing I can answer to the volcanic issue is if we see chimneys originating from a known or suspected source rock, we have higher confidence. So a volcano will have, it may be originating from very deep. You may not see the origin of it. And that might be one way of distinguishing the two.
Okay, Eric has another question. I pass it to you, David.
Okay.
How to play with the test percent? Did you get that?
I'm not at the top of my questions.
I pass it to you. How to play with the test percent and the seismic attribute selection if the first NN result is not satisfactory?
Usually, if the result is not satisfactory, I wouldn't change my test percent. What I would do is go in and look at my misclassifications, and those will come up in red, and you may want to then repick some of your examples that are misclassified. The other thing you can do is look at your attribute set and change that, but generally you do not need to change the percentage you use for testing, unless the only thing I can think of that might be in that case is if you had very few examples to use for your chimney, yes, you may want to cut down that number. But normally speaking, I wouldn't change that number.
Okay, good. Any more questions? Okay, great. Thank you very much, David. That was very useful to everyone. Please, if you have any more question you can think of, you can just send it to our webinar address, which I think you all you all know it. It's thanks for participating with us, and you will be receiving an email with the link by this Friday for our recording session. It will also be in our Facebook and our LinkedIn page. I would like to say for those who are new to our webinar, we have one every month. So please feel free to register for our next webinar. And our May webinar will be talking about a new plugin called NetPay. It's a tool to map reservoir, NetPay, and net sand from seismic inversion data. It's fast to implement and easy to use. The NetPay plugin is developed by ArcSealus, which is one of our OpenTect plugin developers. We hope to have you again with us next month. Thanks everyone, and have a great day.